In my last video, basic explanation of the distortion of the flat Earth map, I went over the two sources of distortion when taking a globe Earth and projecting it onto a North Polar Azimuthal Equidistant projection map. And those were that one was solely north of the equator. You have the issue where the radius of the circle of latitude increases when taking a globe and projecting it onto an azimuthal map. And south of the equator, you have this same issue along with the issue where, say, the circumference of the circle of latitude at 30 degrees north is equal to the circumference of latitude at 30 degrees south on a globe, whereas on an azimuthal map, the circumference of the circle of latitude at 30 degrees south is greater than the circumference of the circle of latitude at 30 degrees north. So reviewing this video, I'm going to go into a more mathematical explanation, and I'm going to show mathematically what's happening. So starting with the circumference, the disparity is created north of the equator. So the first distortion is created by the disparity in the radius. So 2 times pi times radius of a sphere relative to 2 times pi times radius of a circle. There's 2 pi on each side, they cancel each other out, so it comes down to the radius of a sphere relative to the radius of a circle. So suppose we had a sphere that had a radius of 1, and we were trying to determine we need to know the radius of the circle of latitude on the sphere at 45 degrees on a sphere, and then we will determine the radius of the circle of latitude at 45 degrees on a azimuthal map. So solving for the opposite. So here we have the 45 degrees, we know the radius is 1, and we need to know the opposite, and that's when you use SOHCAHTOA. So sine of theta equals opposite over hypotenuse. So sine of 45 equals opposite divided by 1. Multiply both sides by 1. So sine of 45 equals this number. And when we do that, we get 0.7071. So this number is 0.7071 in this instance. And then the second thing we do, the next step is to determine the segment of the circumference of this circle. In order to do this, we apply 2 pi r, which is, so 2 times pi times r, where r equals 1 is just 2 times pi. And then we need to know what portion of this circumference is this. If 45 degrees, you have 360 degrees in the circle, 45 degrees divided by 360 is 1/8. So that in order to determine this line segment here, it is 2 times pi divided by 8. And when we go through that, we find it's 0.785. So now we have those two numbers. We know the radius of the sphere radius and the azimuthal radius at 45 degrees is 0.7071 relative to 0.7854. The difference is here. The difference is here, and then this divided by that equals 11%. So this number is this number divided by this number. And you can see, you can go start from north of the North Pole, working out from there. So this is the equator, 10 degrees north, all the way up, and 10 degrees south, all the way down. And because the North Polar Azimuthal Equidistant projection map is relative to the North Pole, you want to start at North Pole and then 10 degrees out, and then 90 degrees is the equator, and 180 is the perimeter, the circumference. So from there you can use the same calculations and determine what is the sphere radius and what is the azimuthal radius. You take the difference, and this is the distortion from the North Pole all the way to the equator, and that's distortion 1. Okay, distortion 2 has the same issue, along with the issue where the circumference of the circles of latitude are equal on a sphere, given the same degree, 30 degrees north equals 30 degrees south, and it's different on a azimuthal map. So this column is then going to take this azimuthal radius divided by this. So we have 45 degrees south divided by 45 degrees north, and that gives you 2. This is 200%. This is a percentage difference. And I did the same thing. So this is 10 degrees. This is 10 degrees south relative to 10 degrees north. And then so 60 degrees south relative to 60 degrees north, and so on. So that's this column. But this column is just azimuthal radius relative to azimuthal radius. In order to determine the overall distortion, you have to go here, which is then going to include the azimuthal radius of 45 degrees south relative to the spherical radius of 45 degrees north. And that gives you an additional distortion. This is the overall distortion of 233%. This is the distortion caused by the circles of latitude on a sphere being equal and the circles of latitude on an azimuthal map being distorted. So if this is true, at 45 degrees, one should be able to fit this is 200%, so it's 3x. So here we have 45 degrees north, 45 degrees south on an azimuthal map. 3 of these should fit into here. This is a segment of a circle of latitude. And so you take this image here, I cut this out in Photoshop, and I pasted it here, and 1, 2, 3 fit in here. Okay, well what about, say, 30 degrees? At 30 degrees, you should be able to fit, this is 100%, which is a double. 2 of these should fit. 2 30 degrees north should fit in 2 30 degrees south. Okay, 1, 1, 2. And then finally, what about 60 degrees? Well, 60 degrees is a 400%, or 5x. So we take 1 60 degree north, and we paste, and we find 5 of them fit in the 60 degrees south. So this math matches up when comparing the segments of the circles of latitude from north to south to each other. Okay, so points regarding this distortion. So point number 1, 180 degrees south is undefined, since 180 degrees minus 180 degrees equals 0, and one cannot divide by 0. So there is no, this goes up to, this calculation right here does not exist. And point number 2 is, you'll notice that the distortion of, say, 70 degrees and higher south is extreme. However, there are no real land masses until maybe 60 degrees. So you can see that this is 60, you can see that 90 degrees doesn't exist. 75 degrees is still the ice wall. 60 degrees, there are no real land masses, or at least where we're allowed to go. 45 degrees is really where the land masses begin. And you can see 45, it is extreme. You're talking 233% distortion, but it's nothing compared to, you know, at 80 degrees south, you're talking 1600%. 70 degrees south, you're talking 700%. Okay, so in my first video, the width of the United States versus Australia explanation, I measured the width of Australia and United States and compared it, and this is what I came up with. You'll see that I did see the trend, the same trend on the distortion from the globe Earth to the azimuthal map, where the distortion increases as one moves from the North Pole outward. You see the same trend when comparing the width ratios of these countries, but these do not line up perfectly, and I think there's really 3 reasons for this. One is human error, so my measurements weren't exact. Point number 2, the length and width in the first video were measured in straight lines, but the distortions in this video are circles of latitude or curved lines. So these circles of latitude are going to be greater then the distance of the circles of latitude are going to be greater than these straight lines. And then the third reason is that the countries extend over multiple circles of latitude, so the distortion of the width varies depending on which circle of latitude the width was taken. So if you take the width up here, it's going to be less distorted if you take the width down here. And with the United States, so now we can go and look at the, okay, so let's look at Australia. Australia sits between 10 degrees south and 40 degrees south. So the distortion would be between 77% and anywhere from 196 to 233%. And when we compare that to our calculation here, this is 2.3 times with 2.3x, which is actually 130%. So that matches up pretty well. And then we have the United States, which is between 25 degrees north and 50 degrees north. And if we look at that, we see 25, you're looking at 30% distortion. I'm sorry, 20% distortion, and 50 is 8.6%. And we, first of all, one must note that this was taken fairly north of the United States, and the distortion was about a 9% distortion. And finally, so that matches up pretty decently. And then as far as Greenland's concerned, the only latitude, for some reason, they only provide is 72 degrees north. But we can tell from this map, it starts at 60, and it goes up. This is 75, so let's call this 80. And I found it to be about 1.7% distortion. And if we look at 60 as a 4.7 to 0.5% distortion, so that appears to be fairly accurate. So in my next video, I'm going to now take the radius of 1 and apply it to the Earth's radius, and I'm going to determine certain things such as the disparity of the radius of the globe Earth relative to the flat Earth, and from there one can come up with all kinds of calculations as to what this world is geographically.